What is AFM? AFM, or atomic force microscopy, is a way to image and analyze a sample for measuring local properties, like the dimensions of the sample. The AFM measures these properties by raster scanning the sample with a probe, which sends feedback to the sensors and the data is collected. This is unique because it is not limited by optical resolution but rather the size and sensitivity of the probe. Invented in 1986, the atomic force microscope is relatively new and has already undergone much development. The first AFMs were operated in contact mode. In contact mode, the tip, mounted onto the end of a flexible cantilever, raster scans the surface of the sample. The deflection of the cantilever due to the tip-surface interaction reveals the sample surface. Samples can be analyzed in air, liquids, or vacuum. In liquids and vacuum, the absence of strong capillary forces due to a thin liquid film on all samples in air can result in higher resolutions. Biological samples are difficult to scan using contact mode because they are often soft and weakly bound to the surface and therefore can be damaged easily. Non-contact mode was first introduced in 1987, developed in an effort to more accurately image soft biological samples. In non-contact mode, the cantilever oscillates close to its resonance frequency at a small distance, 1 to 10 nanometers, above the surface. Long-range attractive forces induce changes in the amplitude, frequency, and phase of the cantilever and maintain a constant distance during the scanning. Because the force on the sample are much lower in contact mode, even the softest samples can be imaged without damage. Imaging in attractive mode is also possible. The optical AFM version 4 was also developed in 1989. The fourth prototype of the AFM generated interest in commercial development and implementation of AFMs. In 1993, tapping mode was first introduced. In this mode, the cantilever oscillates at its resonant frequency. But unlike non-contact mode, the cantilever taps the surface during the scanning, greatly reducing the damaging lateral forces. Tapping mode in fluids was first introduced in 1994 by the Hansma lab. In the first implementation of tapping mode in fluids, the sample, which sits on a piezoelectric scanner, oscillates up and down and taps the tip at the apex of each oscillation cycle. The amplitude of the piezoelectric is set manually at the beginning of the run, and the tapping force is held constant by a feedback loop. Smaller cantilevers were developed in 1996, allowing higher resolution and smaller scanning times. The Hansma group began developing a new generation of AFMs that would utilize these smaller, lighter cantilevers. For biological samples, desirable cantilevers have a higher resonant frequency, and therefore a higher scanning speed, and a lower spring constant. This is most easily achieved by decreasing the mass of the cantilever. Recently, cantilevers have been fabricated on the order of 9 to 40 millimeters in length and with resonant frequencies on an order of magnitude higher than commercially available cantilevers. The next prototype was a small cantilever AFM version 5. The major difference between AFM and the previous AFMs lie in the optic design of the microscope. This prototype has a much smaller laser spot, allowing for the smaller cantilevers to be used. It also includes an integrated illumination source, essentially combining an optical microscope and an atomic force microscope in the same piece of equipment. Improvements in instrumentation and the understanding of atomic force microscope has led to its wide use in many fields in engineering, material science, and biology. Just like any other tool, an atomic force microscope's usefulness has limitations. When determining whether or not analyzing a sample with an AFM is appropriate, there are various advantages and disadvantages that must be considered. AFM has several advantages over the scanning electron microscope, SEM. Unlike the electron microscope, which provides a two-dimensional projection or a two-dimensional image of the sample, AFM provides a three-dimensional surface profile. Additionally, samples viewed by a AFM do not require any special treatments, such as metal or carbon coatings, that would irreversibly change or damage a sample. While an electron microscope needs an extensive vacuum environment for proper operation, most atomic force microscopy modes can work perfectly well in ambient air or even liquid environment. This makes it possible to study biological, micromolecules, and even living organisms. In principle, AFM can provide higher resolution than SEM. It has been shown to give true atomic resolution in ultra-high vacuum UHV, and more recently, in liquid environments. High-resolution AFM is comparable in resolution to scanning tunneling microscopy and transmission electron microscopy. A disadvantage of AFM compared with a scanning electron microscope, SEM, is a single scan image size. In one pass, the SEM can image an area on the order of a square millimeter, with depths of field on the orders of millimeters, where the AFM can only image a maximum height on the order of 10 to 20 micrometers and a maximum scanning area of about 150 by 150 micrometers. One method of improving the scanned area size for an AFM is by using parallel probes in a fashion similar to that of millipede data storage. Scanning speed of an AFM is also a limitation. Traditionally, an AFM cannot scan images as fast as an SEM, requiring several minutes for a typical scan, while the SEM is capable of scanning at near real time, although at relatively low quality. The relatively slow rate of scanning during an AFM imaging often leads to thermal drift and image, making the AFM microscope less suited for measuring accurate distances between topographical features on an image. However, several fast-acting designs were suggested to increase microscope scanning productivity, including what is being termed video AMF. AFM images can also be affected by hysteresis of the piezoelectric material and crosstalk between the X, Y, and Z axes that may require software enhancement and filtering. Such filtering could flatten out real topographical features. However, newer AFMs utilize closed-loop scanners which practically eliminate these. How do you use it? A sample must be loaded into the chamber, and a probe must be carefully lowered to just above the surface. Too far away, and there won't be any measurements. Too close, and the probe tip could break. Once loaded, an appropriate scan speed must be chosen for your required accuracy. What kind of data? There are two common probing techniques: constant force and constant distance. With constant force, the probe height is adjusted if the force changes so that it remains constant. This is useful in making force measurements on a sample. For constant distance, the probe height is adjusted to maintain a constant distance from the sample. The data is then used to create an image. The required height change is so small and so precise that the piezoelectric material must be used to allow for precise and small changes. What kind of analysis? The acquired data is most commonly analyzed in a software called Gideon. Surface roughness, dimensions, heights, and such can then be quickly analyzed from the data using tools provided in the software.
Thank you for watching the tutorial on atomic force microscopy. We hope you find this useful and look forward to seeing you grab your own samples very soon.